Okay. So I should see if I get any webmail. Okay. Yes. Okay, so this is our third in a series of streams on reviewing for MAE 106. So we're going to be covering the topics of, let's have conditional probabilities and Bayes' theorem. We're going to talk about random variables, what they are, what's the probability distribution of a random variable, what's the expected value of it, the variance, the standard deviation. And then we'll also discuss the two special probability distributions that we studied in class, which were the binomial distribution and the normal distribution. So also some paper slide. Okay, so we'll start off with a couple of questions that kind of select to kind of give an overall these are kind of questions kind of that you're typically going to see. So here's an example. What is the probability of drawing without replacement 2 kings in a row from a well-shuffled deck of cards? And this is going to be using the idea of conditional probability. Okay. So remember, in conditional probability, that the probability of some event F occurring, given that I know E has occurred, is equal to the probability of E and F over the probability of E. And this is provided that the probability of E is not equal to 0, because then it's not defined properly. You will also need another form of this. We can also rearrange this formula so that I can bring this over to the left-hand side, so that I get that the probability of the intersection, EF, is equal to the probability of E multiplied by the probability of F given E. Okay, so these are two equivalent forms that we'll be using a lot when we're talking about conditional probability. So in this case, what is the probability of drawing without replacement 2 kings in a row from a well-shuffled deck of cards? So here is, let E be a king on the first draw. And we'll let F be a king on the second. Draw. Okay. So what this is asking is the probability of drawing 2 kings in a row. So it's the probability of drawing a king on the first draw and drawing a king on the second draw. And again, because this is without replacement, we're going to be using conditional probability. So in this case, we're going to have the probability of E multiplied by the probability of F given E. Okay, so this is the probability that we picked a king on the first draw, and multiplied by the probability that we pick a king on the second draw, given that the first card was a king. Okay, so the probability of this occurring is, well, there's 4 kings and there's 52 cards. On the second draw, well, if we assume that one of the kings has already been selected on the first draw, it means that there's going to be 3 kings remaining on the second draw, and we're going to have not 52 cards because we've already picked one of them. We're left with 51. Okay, so then that becomes, well, we can simplify this a little bit so that we have 1 and 4. I think that's right. So that's 4. Whoops. 4 over 52. No. I made a mistake here. Anyways, if I just do 12 over 52 times 51, that gives me 2,652. Could I do that in lowest form? Let's think about that. That's 256. So, yeah, I could. This just reduces down to 1 over 221. But this is fine. If you leave it in this form, I'll understand what you mean. So, again, make sure that you have a therefore statement. So, therefore, the probability of drawing 2 kings in a row is 12 over 2,652, or 1 in 221. Okay, so here's another question using conditional probability as well. So now this time I have an urn. It contains 6 red and 9 balls. So that means in total 6 plus 9 gives me 15, so 15 balls in total. We draw 2 balls from the urn without replacement. So again, we're going to be using some idea of conditional probability. Assuming that each ball is equally likely to be drawn, what is the probability that both balls are black? So what I could do is I could do it with a tree diagram, and this is what I'm going to do. So on draw 1, I'm going to have to be doing this without a ruler. Okay. So on the first draw, we could have red and we could have black. Same thing again on draw 2. I could have red and I could have black. Same thing again, red, black. So the probability of picking red on the first draw is 6 over 15. And for picking black, it's 9 in 15. Now here, this is the conditional probability that I've picked red on the first draw and the probability of picking red on the second draw. So on the second draw, I only have 14 balls left. And if I picked one of the reds, I'm going to only have 5 remaining. And if I didn't pick a black, if I didn't pick a black on the first draw, then that means I'm going to still have 9 black on the second draw out of the possible 14. Similarly, I have black on the first draw. This means that I'm going to have out of the 14 balls, I'm going to have all of the 6 red, and on the black, I'm going to have 8 remaining black balls because I picked one of them on the first draw, left with 8 over 14. Now it says, what is the probability that both drawn balls are black? So in this case, I'm actually interested in this one right here. So I'm interested in the probability that I drew black on the first draw and I drew black on the second. And that's just equal to multiplying down these rows now. So I get 9 over 15 multiplied by 8 over 14. So 9 times 8 is 72. And 15 multiplied by 14 gives me 210. So that's the probability. So therefore, the probability that both balls are black is 72 over 210. Okay. Now this is one that I covered in class, and I think it's good enough that we could even review it again as an example. So this was from my book, page 343. So, just trying to... So the important thing is this is a word problem. You have to parse what kind of information you're given and what it's asking you to find. Okay, so if a black hat hacker has gained access to a computer network, the network software alerts the administrator with probability 0.95. The software sometimes generates a false alarm, and that is, there is an alert when a hacker is not present in the network with probability 0.1. We assume that a hacker is in the system with probability 0.03. So what is the probability of no hacker and a false alarm? And B, the software not detecting a hacker even though there is a hacker in the network. So the first, there's two things going on. There is the the hacker that could be in there, and then I have the kind of software that's going to generate me the alert. So what I'm going to do is let E denote a hacker in the system. Okay, and I'm going to let f denote the software generates an alert. Okay. So in that case, we can start drawing our tree diagram because this is going to be conditional. So first thing I have is, here's the probability of E and E prime. Okay, so we're told, first off, I use green in this case. We assume a hacker's in the system with probability 0.3. Okay, so the probability that the hacker's in the system is 0.03. So what does this mean? Well, it means then the complement is 1 minus 0.03. So the probability that a hacker isn't in the system is 0.97. Okay. The next part, I have F, which is going to be, it generates an alert, and this one doesn't. Alert, and no alert. Okay. So, reading back the question, if a black hacker has gained access to the network, it alerts this network software alerts the administrator with probability 0.95. So the network alerts the administrator with 0.95, and this is if there is a hacker in the system. So going back to our tree diagram, there is a hacker in the system. It's going to give me an alert. So this is 0.95. Okay, which means that by the complement, the probability that there's a hacker in the system and I don't get an alert is going to be 0.5 or 0.05. And again, this is just the complement, that 1 minus 0.95 equals 0.05. Okay. And there's one more piece of information in this that we can use, and that is right here. The software generates a false alarm. So that is if the hacker is not present in the network, then it generates an alert with probability 0.1. So there's no hacker in the system, and the software still generates an alert, and that happens 0.0 or 0.10 time, and then this is by the complement 0.9. Okay. So part A is asking me, no hacker, what is the probability that there's no hacker and a false alarm? So this is no hacker and there is a false alarm. Okay, so I get to follow this branch right here. Okay, so for part A, I have the probability that there is no hacker and there is a false alarm. Okay, so using our conditional probability, that's the probability of E prime multiplied by the probability of F, which is that there is alert given that there is no hacker. And so that equals 0.97 multiplied by 0.10. And that gives me a probability of 0.097. So, therefore, let's see, 0.97. Yeah. Okay, so therefore, the probability of a false alarm, or sorry, of no hacker and a false alarm is about 9.7%. Okay, so this is this area right here. Okay, so for B, this is going to go back to this question here. The software not detecting a hacker, even though there is a hacker in the system. So, what this is asking for is the software not detecting a hacker, even though there is a hacker in the system. So there is a hacker in the system, but the network isn't detecting it. So the software isn't detecting it. So instead, now this time, we're going to be following this branch here. So for part B, that is the probability of E intersect F prime. So again, that's equal to the probability of E multiplied by the probability of F prime, given that there is an E. So I write this down, I get 0.03 multiplied by 0.05. Okay, so that's 0.03 multiplied by 0.05 gives you 0.0015. So therefore, the probability of not detecting, well, the probability of the software not giving an alert, even though there is a hacker, is about 0.15%. Okay. So this again is a great example of showing here there's lots of information in here, and that you need to draw a a probability tree diagram, and from that you can figure out which events that you need to calculate. Okay. Oh, these are again another classic type of question that you'll may or may not see. Let's see. There we go, an example. A box contains 3 coins. Coin A is fair, which means that the probability of heads and tails is equal. So probability of getting heads is 1/2, probability of tails is 1/2. Coin B has 2 heads, so the probability of getting heads is 1 in this case, and the probability of getting tails is 0. And coin C has been modified such that the probability of heads appearing is 1/4. So that means that the probability of tails is going to be 3/4. An experiment consists of selecting a coin at random, tossing it, and observing the side that lands uppermost. If the coin was tossed showed heads, what is the probability that it was the two-headed coin? Okay. So this is going to be an example of Bayes' theorem because we're observing the effect and we're trying to we observe the we have an effect and we have the cause. So what we're seeing is if the coin was tossed, showed heads. This is the effect that we're observing. What is the probability that it was a two-headed coin? We need to try to figure out what that cause was, because there in fact is 3 different coins that could have caused this effect, and we need to calculate what that probability is of that two-headed coin causing this effect. So what we do is we have our first stage. And in the first stage is we're going to be randomly selecting a coin. Okay, so you can have coin A, you can have coin B, and we also could have coin C. Okay, and what we're going to do is we're going to be selecting it at random. And now we're going to be assuming that this randomness is that we're equally going to be selecting the coin. So this means that if I have this here, if I randomly select it, it means that I'm going to have, I'm going to assume that there's equal probability for each of these. So the probability of selecting coin 1 or coin A is going to be 1/3. The probability of selecting coin B is 1/3. And last, I'm going to be selecting coin C with 1/3. Now in stage 2, I have either heads or tails. I can have heads or tails. And last, I can have heads or tails. And this is stage 2. Okay. So let's go back. Coin A is fair. So this means that the probability of heads and the probability of tails is going to be 1/2. 1/2. The probability for B has 2 heads, which means that it's going to, with certainty, land on heads. So the probability of that occurring is 1, and the probability of getting tails is 0. And last, I have a coin C that's biased. It's going to be landing on heads 1/4, which means by the complement, it's going to be landing on tails with 3/4 probability. Okay. If the coin was tossed, showed heads, so this is our given. What is the probability that it was a two-headed coin? So this was the coin B. So this was coin B. So what's the probability that it was coin B, given that we saw heads? Okay. So in this case, we're going to we can use probability, our conditional probability. So that is that you picked coin B and that you had heads all over the probability of heads. Okay. So the probability of picking coin B and getting heads is following this one right here. Okay, so the probability of that is 1/3 multiplied by 1. Okay, and then to calculate, so that's the only time that I have that. Now to calculate the probability of getting heads, I have these other, I have this case, I have this case, and I also have this case. So following, I have this case here. So the probability of getting this case here is 1/3 multiplied by 1/2. Okay, or I could also have picked coin B, 1/3 multiplied by 1. And then last, I could have picked coin C and then got heads with 1/4 probability. Okay. I'll switch back to just using black. So I get 1/3 over, I get 1 in 6 plus 1/3 plus 1/12. Okay, so what I should do then is, to solve this, I should write this all over, I'll write this over the largest denominator here. So I can convert this to 12. So I'm going to be multiplying this 3 by 4, and then this gives me 4/12. 12. So I'm multiplying this by 2, so I get 6 times 2 is 12. So 1 times 2 is 2, and then I have 12. Again, so this is going to be multiplying by 4, so I get 4 here, and I'll leave this unchanged so that I have 4/12 divided by, now I have 2 plus 4, which is 6 plus 7/12. Okay, now I have two fractions, so I can have 4/12 multiplied by the reciprocal, which is 12/7. The 12s cancel, and I'm left with 4/7. Okay, so therefore, the probability of coin B being selected, given that it showed heads, is 4/7. Okay, so just to review that, what I've done is I observed an effect. I wanted to figure out what the cause was. And because there's heads, I have 3 causes here. These 3 coins could have caused that effect of getting heads. I can calculate the probability of it was coin B, given that it was heads. And so, again, here's our conditional probability. It's the probability of B intersect H over the probability of getting H. So again, this was our case that we wanted over all the possible cases where we had heads, and we got that the probability is 4/7. Okay. Oh yes, we should talk about random variables. Sometimes we don't care about what the outcome is. We kind of want a special value for it. And we start to get into the idea of random variables. So for instance, let's say that I rolled 2 dice. So if I rolled 2 dice, then I could have the sample space where I have 1, 1, 1, 2, 1, 3, 1, 4, all the way up to, 6, 6. By the way, what is the number? What's the cardinality of the sample space in this case? So I'm rolling 2 dice. Well, in total, there would be, there's 6 choices for the first one, and there's 6 choices on the second one, so we're going to have 36. But, when people are throwing craps, they don't care if I rolled a 1 on the first throw and I rolled a 2 on the second throw. No, what they care about is the sum of the dice. And that's what the random variable is we assign numbers or values to the outcomes. So, for instance, I keep talking about craps. We're looking at the sum of the dice. So, I have my I have my 36 outcomes, but again, that crap shooter is interested in what the sum is, not necessarily what the outcome is. So what I could say is, let's let x denote the sum of the 2 dice. So I get, if I just fill in my table here, okay? So what I could do is I could ask, what's the probability of getting a sum of 2 dice? Well, in this case, there's only one case out of the possible 36. So that is 1 in 36. The next thing I could ask is, what's the probability that x equals 3? Well, the probability of that is, well, there's only 2 cases in that instance, so I get 2 over 36. I can calculate this for 4. So I have 3 cases in that instance. 3 over 36. And I think you're starting to see the picture. Now if I calculate 5, there's 4 cases. The probability that crap shooter throws a sum of 2 dice is 6. 1, 2, 3, 4, 5. Lucky 7. Why do they call it lucky 7? Probably I don't know why, because it's not exactly something rare, because it shows up the most. 1, 2, 3, 4, 5, 6. 6 out of 36. Good. So here's 8. 1, 2, 3, 4, 5. 5 over 36. I'm going to finish this up so that I have the probability of x equals 9. That is 1, 2, 3, 4 over 36. The probability of x equals 7 is 3 over 36. Probability of x equals 11 is 2 over 36. Lastly, x equals 12 is 1 over 36. Okay, so what I've done is I've actually written out a probability distribution. I've done the probability distribution of x, so that anytime that I have some value of x that I want to calculate for the big X of our random variable. The probability of getting 2, that's 1 in 36. 3 is 2 in 36. 4, 3 in 36. And the thing that we should point out, and this is really important, is that when you look at a distribution, the sum of the distribution should be 1. Okay? If you don't have that, then it's not a proper probability distribution. Or in other words, you might have made a mistake. Okay? So when I sum these all up, I get, well, here's 2. I got plus 4, so there's 6, plus 9. 6 plus 9 is 15. 15 plus 8. 15 plus 8 gives me 23, plus 11. Oops, maybe I didn't write. Oh, yeah. 2 plus 3. 1 plus 2 is 3. 3 is 6. Plus 4, there's 10. So I have 10 on this side as well. So 10 plus 10 is 20. I got 30 now, plus 6. So there's 36. So again, this is an important key point. I don't know if I can make this any more redder, or this is important. The sum of a probability distribution is 1. Okay, or in mathematical notation, the sum of all the possible values of x, that the probability of those is equal to 1. Okay, so as we go into this question, we are given this probability distribution. The first thing that we're asked is, what is A? And here's A right here. And like I said, the probability, the sum of the probabilities has to equal 1. So this means that I have 1/4, or sorry, 1/5 plus 2/5 plus A plus 1/5 plus 1/5 should all equal to 1. So I have 1, 2, 3, 4, 5. Oh. 1, 2, 3, 4, 5. Well, so I have 5 over 5. So I have 1 over here plus A. So I have A equals 1 minus 1. So I'm left with 0. So the probability in this case is A equals 0. Okay. The next part is what is the expected value of x? And the formula for that is the expected value of x is equal to the sum of all the possible values of x, so of x multiplied by the probability of x. Okay, so that means that I have 1 multiplied by 1/5 plus 2 multiplied by 2/5 plus 3 multiplied by 0 plus 4 multiplied by 1/5 plus 5 multiplied by 1/5. So I get 1/5 plus 4/5 plus 0 plus 4/5 plus 5/5. Okay, so I get 9. 9 plus 5 is 14 over 5. And, you know, that's equal to 2.8. Sorry. Just needed some water. Okay, the next one is what is the variance of x? Now, we can calculate this using two ways, but what we've been generally using in class has been that the variance of x is equal to the expected value of x squared minus the square of the expectation. Okay, so that means what that means is we need to calculate this value right here. So the expectation of x squared is equal to the sum of all x, where we have x squared multiplied by the probability of x. Okay, so I have to use this. Again, I'm going to square these values. So 1 squared multiplied by 1/5, 2 squared multiplied by 2/5, 3 squared multiplied by 0, 4 squared multiplied by 1/5, 5 squared multiplied by 1/5. So what I'm going to basically do is take this line right here and then just add those squares on that. So 1 squared multiplied by 1/5 plus 2 squared 2/5 plus 3 squared multiplied by 0 plus 4 squared multiplied by 1/5 and 5 squared multiplied by 1/5. So 1 squared is 1 multiplied by 1/5, so it's 1/5. 2 squared is 4. 4 multiplied by 2 is 8/5. Plus I got 0 plus 16 over 5 plus I have 25 over 5. Okay, so then I just add up those values. I have 1 plus 8 plus 16 plus 25. So I get 50 over 5, which gives me 10. Okay. So last but not least, I get that the variance of x is equal to 10 minus the expectation squared. So 2.8 squared. So 2.8, 2.8. 8 times 8 is 64. 8 times 2 is 16. 16 plus 6 is 22. Okay, and then the same idea again. I got 2 times 8 is 16. Carry that 1. 2 times 2 is 4 plus 1 is 5. So I get 4, 8, 7. So 7, and then 1, 2. 1, 2. Good. So 10 minus 7.84. And I'm left with 2.16. Oops. There we go. Okay. And the last question is what is the standard deviation? And all that is that the standard deviation is equal just to the square root of the variance. So it's just the square root of 2.16. then that's it. Because we have the square root of 2.16, it's kind of difficult for you to calculate that, so we don't expect you to do that on the exam. So just leaving it with square root 2.16 is fine. Now, some things that we kind of expect you to be able to do is, you know, if it's a perfect square. So again, if I have the square of 25, well, that's 5. You know, the square of 16, 4. But something like this is a little bit tricky. So we don't expect you to do that. Okay. Okay, so it is known that 7% of computer chips produced by a machine are defective. A. Find the probability that out of 30 chips produced, exactly 3 will be defective. And the second part of that question, 3 or more will be defective. Okay, so the first thing I'm going to do is let x be the number of defective chips. In a batch of 30. What I'm going to say is that we're going to assume that x is binomially distributed. Okay, so like I was talking about in class, you probably will be asked to justify why it is binomially distributed. And in this case, we're going to assume that they're independent. That the chips themselves, the probability of one chip being defective doesn't affect the probability of another chip being defective. We're going to also say that there is two outcomes that we're interested in. And we usually consider them as a success or a failure. And I can put these little quotes in, because in this case, a success, we're actually looking, it's called a success if we find something defective. So it's a success if we finding a defective chip. And similarly is not finding a defective chip. Okay, and the third one is that each chip, or well, the testing of it, each trial is identical. And so in this case, that's because the probability of this occurring is 0.7. So again, the probability isn't changing from chip to chip. We're going to assume that the probability of a defective chip is 0.07. Okay, so part A, without me doing too much of the calculations, I'm just going to write them out. So remember that if we're following a probability distribution that's binomial, the probability that x equals little x, or the value of x, is equal to, we have n trials, and we're going to choose x of them, multiplied by the probability of success to the exponent x, and then multiplied by the probability of failure to the exponent n minus x. So when it says find the probability that out of the 30 chips produced, exactly 3 will be defective, in this case here, 30 is our number of trials. We have 30 of them. And we also have here the probability is equal to 0.07. Okay. So we're asked to find exactly 3. So in that case, to find exactly 3, A, so the n is equal to 30, p is equal to 0.07. So using my formula here, the probability of the number of defective chips equaling 3 in the set of 30 is 30, choose 3, multiplied by the probability of success, which is 0.07, to the 3, multiplied by the probability of not finding it, which is 0.93. And then we have 30 minus 3, which gives us 27. Okay, and then you would calculate that. On the exam, you should have fairly straightforward numbers. So you won't have to worry. But I'm just going to write that out and leave that there. For the second part here, the probability of exactly 3 or more means that I want the probability of x greater than or equal to 3. Okay, now I could do x plus the probability of x plus 3 plus the probability of x equals 4 plus all the way up to the probability of x equals 30, and that is too much work. So the other way that we could do this is to take indirect reasoning, which is we're going to take 1 minus the probability of x less than 3. And so that equals 1 minus, and then we have, you know, those cases of x equals 0 plus x equals 1 plus x equals 2. Okay, which is a lot shorter than having to calculate 3 through 30. I just have to calculate 0 through 2. And again, you just apply the same formula again. So I have 30 choose 0 multiplied by 0.07 to the 0, 0.93 to the 30 plus 30 choose 1. Okay, and so you can calculate that. That would be with a calculator, but again, on the final exam, you would have something that's easier to calculate. Part B. Part B asks us, what is the expected number of defective chips out of 30? And remember, because we got this, because we're using a binomial distribution, I mean, you could do this, you know, all x multiplied by the probability of x times x. You know, you could do that, but then that means you're going to have 1, and then you have the probability of x equals, whoops, we should 0, 0, plus the probability of 1 multiplied by the probability of 1. You know, all the way up to the probability of x equals 30 multiplied by 30. So that's a lot of calculation. We have a shortcut. Because it is a binomial distribution, there is a simple formula, which is just n multiplied by p. So there was 30 chips, multiply the probability of success, which was 0.07. So 0.7, so it's 330 times 7. So again, that's, you get 21. Then there's a 0, 1, 2, 1, 2. So I got the expected value is 2.1. So 2.1 chips out of 30 are expected to be defective. Okay, I should also mention that in part C then, they ask us what the variance is. And again, instead of doing the calculation for the variance, we have a shortcut. So the variance is this. It's the probability of n multiplied by p multiplied by the probability of failure. So the number of trials multiplied by the probability of success multiplied by the probability of failure. So that I get 30 multiplied by 0.07 multiplied by 0.93. So again, I got 2.1 multiplied by 93. So 93, 21. So I get 93, 0, 2, 6, 18, 3, 15, 9, 1. And again, because I have 0.9, and there's 1, 2, 3, 1, 2, 3. So the variance is actually equal to 1.953. So, and that's it. Okay. Okay, so we did binomial distribution. The last one that we covered in class was the normal distribution. And I don't think I got to cover this one in class. It's kind of nice that I get to have this for the review. An IQ score, or intelligence quotient, is derived from a test, usually administered by psychologists to human subjects to determine their intelligence. A person with an IQ score of 100 has average intelligence. An IQ score follows a normal distribution where the expected value is 100. So you expect, again, an average person to be having a score of an IQ score of 100 with a oops, clearly I screwed up on the typewriter. Standard deviation is 15. If a person is randomly selected, what is the probability that this person's IQ score is between 85 and 115? Okay. So just to give you an idea of the normal distribution, there it is. As best as I could draw it. So in the middle here is the expected value. Okay, so in this case, we have an expected value of 100. And we are also told that the standard deviation. The standard deviation is the distance, excuse me, the distance from the expected value to the point of inflection in the curve. And the variance in this case, we're told, is 15. Now the area under a normal distribution is equal to 1. And what we need to do is we need to figure out what this area is between, say, 85, in this case for part A, and the area between 115. So here's the area that we want. Okay. Now what we need to do is we want the probability. So what we should do, and it's important, let X denote a student's score. Or sorry, not a student's score. I keep thinking denote a person's IQ score. Okay? So in this case, we want the probability that X is between 85 and 115. So the one way that we could do this is to get that, I could find all the area from the left-hand side up to 115, and then I could subtract the area up to 85, which is all this area here. So again, if I have all this area here and I take away this area right here back, then I'm just left with the area in between. Which is what we want. Okay. So we can break that down in those same kind of steps. I have the probability of x less than 115 minus the probability of x less than or equal to 85. Okay, we still have a problem because I want to use this, and this is what you're going to have on the exam. This is the standard normal table, and in a standard normal table, as you can see here, the expected value is 0, and in this case the standard deviation is equal to 1. So they're not the same random variable, but we can convert this x to this z. And we can do that using this formula right here. Okay, so it's z is equal to x minus mu over sigma. Okay. So in that case, I can convert it from x to z by, I have 115 minus mu, which is 100, over 12. Okay. The next one I have is the probability of x in this case I'm going to be converting it to z. So I have 85 minus 100 all over 12. Okay. So I have 15 over 12, which gives me 1.25. And then I have 85 minus 100, which gives me negative 15 over 12. So that gives me the probability of z less than or equal to minus 1.25. Okay. So now I look up my values. I want this value for 1.25. So here's 1.2, and then I look for the 5 in this column here. So I get 0.8944. 0.8944. And then I need negative 1.25. So with the magic of science, I can zoom in. .25. Oops, zoomed in too far. So 1.25. So here is 1.2, and so 1.2 right there, right about here, and there's the 0.5. So it's 0.1056. 1056. Okay, and then you just perform that subtraction. 0.8944 minus 0.1056 gives you 0.7888. So therefore, the probability that someone has an IQ score of 85 between 85 and 115 is 78%. Okay. Okay, so for part B, we want the probability of x is greater than or equal to, greater than 125. Okay, so again, we can do the same. First what we should do is take the complement to get it as a less than or equal to sign. So 1 minus probability of x less than or equal to 125. Then the next I can convert this to a z random variable so that I get 125 minus 100 over 12. So I get 1 minus, and so that's 25 over 12 gives me 2.08. Okay, so again, I can look this up in my Z table. 2.08 2.0. Okay, and 0.8. Okay, so I got 0.9812. 0.9812. Oops, I'll zoom that out. Okay, so then 1 minus 0.9812 gives me 0.0188. So therefore, the probability that someone has an IQ above 125 is 1.88%. Just as a small remark, you know those people who do those IQ quizzes on Facebook and they say, oh, I just got, an IQ of 140. The probability of that is really small. I mean, the probability of them having an IQ above 125 is already really small. It's, close to 2%, which is, every 2 in 100 people that you're randomly going to meet are going to have an IQ over 125. So again, the probability is quite slim. It's probably even more if you did it with, let's, instead of doing below 50, let's do that with 140. Some people say you have 140. And you should just ignore them because the probability is quite low. And if you have multiple friends who have it, I mean, basically those online probabilities or the online IQ scores are, I would almost say, bogus. So let's say that they're got a score again north of something 145. So the probability of that is, we can do the same idea again. The probability is 145 minus 100 over 12. So that you get the probability of x is less than, so you get 45 over 12, which is 3.75. And that's, 3.75 is so high that I don't even have this on the table. 3.75. It's not even here because we only go up to 3.5. So, just a second. Probability of a Z score. Z equals 1.3, equals 3.75. I can punch that in, hopefully. I mean, the chance of that occurring is really, really, really small. It's 0.000. Oh, I'm just trying to count how many zeros I have. 0, 8. Okay, so that's the probability of that occurring. So actually that should be 9999. So again, the probability of that occurring is really small. We're talking like 0.00002. 1, 2. So the probability is like 0.002% that someone has an IQ over 145. Okay. And last question, and then we're all done. Let x be normally distributed with an expected value of 1.5 and a standard deviation of 2.1. Determine the value of x such that x is less than or equal to x is equal to 0.7517. Okay. So again, we want this value of x. Okay. Okay, so what I can do is I know that the value of z less than z equals 0.75. That what I do in this case is I look at my normal distribution table 7517. So what I do is I look through these values 7517. So I have here that value is 0.68. So that in case here is equal to 0.68. Okay. Now, to convert this z back to an x, what I need to do is use this formula again. So I have z equals x minus mu over sigma. I can rearrange so that I have z multiplied by sigma is equal to x minus mu. And then lastly, I have x equals mu plus z sigma. So x equals, I know that it's 1.5. Plus, I have the z value, which is 0.68, multiplied by the standard deviation of 2.1. So in this case, my value is 1.5 plus I have 0.68 multiplied by 2.1. So 0.68 multiplied by 2.1 is 1.428. Plus 1.5 gives me 2.928. Okay, so therefore the value is 2.928. Okay, so again, this concludes my series that I've been giving on a review for MAE 106. We've covered lots of topics. We've covered logic, we've covered counting, we covered probability. I hope this has given you kind of a nice overview of the entire course so that it gives you a good grasp of it when you're going into the exam tomorrow. My name is Richard Kaur. Thanks again for tuning in for this live cast. I appreciate you guys giving me feedback, and I wish you the best of luck on your final exams. Take care. Good night.